All right, so in this section of the lecture, I would like to finish the proof that RK is complete, and we'll also look at the Bolzano-Weierstrass theorem for RK. All right, so I'm just going to jump right into this. So so last time we proved the lemma about convergence and Cauchy, the Cauchy criterion for sequences of points in RK. So we'll just use that now. So this is theorem 13.4. Hold on. So RK is complete as a metric space, because remember, the definition of completeness for metric spaces has to do with the convergence of Cauchy sequences, nothing to do with suprema, right? It's only for the special case of just R itself where those two concepts end up being the same thing. But there's no concept of suprema for subsets of RK, right? Okay, so this is actually very easy now that we have the lemma. So let X, say n like that, be a Cauchy sequence in RK. Then so then by the lemma we just proved X and J is Cauchy for each J, right? So again, here we're thinking of this as a sequence where J is constant and N changes, right? But then there's K of these different sequences for each value. There's one for each value of J, right? There's a sequence for each value of J. So then, you know, XJN converges in R for each J. This in R is sort of unnecessary for me to say. I'm just trying to remind you that this is a sequence of numbers in R. So we already have a theorem from a while ago, right? That any Cauchy sequence of real numbers has to converge, right? So then, by the lemma, again, because now we know that each coordinate sequence converges, remember the lemma also stated that when you know that each coordinate sequence converges, you know the overall sequence converges, right? So X and converges. And that's what we wanted to show, right? Every Cauchy sequence in RK converges, okay? So that's completeness. Now let's look at the Bolzano-Weierstrass theorem. So if you remember the Bolzano-Weierstrass theorem, so recall, I'm just going to call it the BW theorem for R, says every bounded sequence has a convergent subsequence, right? Now, we haven't actually strictly defined what it means for a sequence of points in RK to be bounded, okay? So let's just define that. So X and sequence in RK to be bounded if there exists a number such that, you know, greater than 0, I guess, such that, let's see, how do they say it? They say the maximum, oh, they actually define it for sets. Okay, well, same thing, it doesn't matter. Such that X and J is less than or equal to M for all n and j, right? So of course, j only goes between 1 and k, but n ranges across the whole sequence xn, right? So their definition is for sets. So S is, so if S is a subset, such that x, j is less than or equal to m for all x in S. So same concept, really. Okay. Yeah, so this is boundedness. So now the Bolzano-Weierstrass theorem for RK reads as follows. Let x and, or sorry, let x, let's keep using the superscript notation, be a bounded sequence in RK, then xn has a convergent subsequence. Okay, so let me just illustrate the proof of this. All right, so sketch of the Bolzano-Weierstrass theorem for RK. All right, so suppose x n is bounded, right? First of all, this means that each coordinate sequence, right, is bounded. This is hopefully fairly clear that if the overall sequence is bounded, then when you fix your attention on any one of the coordinates, the sequence you get of those coordinate values is also bounded. So for each j, right? So remember, when we talk about these sequences, j is constant, right? For any one of these sequences, you fix a value of j and then you let n vary, okay? But of course, when you change j, you switch around between the different sequences. So there's like there are k different sequences here, one for each value of j. So let me sort of draw out. I'm going to make a cut because it'll take a little bit of time to draw, but I'll draw a picture for you. Okay, so here are some values in our sequence, some of the points in our sequence listed off. All right, so sorry, when I said picture, I really meant I'm just going to write out a bunch of points in the sequence. And then I'm going to show you how we select our subsequence, okay? So the first thing is, okay, let's consider x1 n, right? So the very first coordinate sequence, okay? The first coordinate sequence we know is bounded. So when j is 1, we get a sequence that's x1 n. So we have like x1, 1 over here, x1, 2 over here, x1, 3 over here, so on, right? All of the x1s form a sequence which we know is bounded, all right? So by the Bolzano-Weierstrass theorem for R, we know there's a subsequence of that sequence which converges, okay? So I'm gonna pick out some terms. So let's say we pick that one, and we pick this one, and we pick this one, and we pick this one, and maybe this one, and this one. Okay, so the red terms, actually, let's see. So, okay, a term circled in red, that sequence, the subsequence of red terms, is the sequence where x1 is the subsequence, sorry, where x1 n converges. So this exists by the Bolzano-Weierstrass theorem for R. So we just picked a subsequence of the overall sequence of points where we're guaranteed that the first coordinate of all the points in this subsequence will converge, because we knew that that first coordinate sequence was bounded. So we can do that, okay? So we picked one subsequence of this. Now, for this one, we only know that the first coordinate converges. We don't know anything about the other coordinates. But what we can do is we can pick a subsequence of this subsequence to get another sequence where now the first two coordinates will converge. So I'm going to do that one in a different color. So let's say we pick this one, right? And let's say this one and this one, and then we leave out that one. Okay, so now what we have is, okay, so we'll have things that are circled in red and then green. This is a subsequence where x1n and x2n, right, both converge now. So again, that exists by the Bolzano-Weierstrass theorem, because now we just have this one subsequence where the first coordinate converges, but still the second coordinate of these terms are all still bounded, right? So there has to be a subsequence of this red sequence. There's a subsequence of the red sequence where the second component converges. But the red sequence also already guarantees that the first component converges. So when we pick the red and green subsequence, that guarantees that the first two will converge, okay? And then let's do one more. So we can keep going like this, right? So now I'm gonna pick this one and this one, right? And then so on, right? Obviously I can't pick any of these because I didn't pick them for the green subsequence. So I can only look at the red and green subsequence now, and I can pick a subsequence of that where, where the third component converges. So now I have this, red, green, blue. Now this is a subsequence where the first three components converge. Okay, so basically the idea is just continue picking subsequences. So each subsequence you pick is a subsequence of the previous subsequence that you had. Like this, k times, right? We only have to do this k times, then all the components converge. Okay, so it's key here. It's key here that there are only finitely many components, right? That this k is finite. That's what actually lets us do this, because we only have to do it a finite number of times, and we'll actually end up with a subsequence this way, like a real subsequence, which guarantees that all the components converge at the same time, right? So then by the lemma, the subsequence converges, right? The subsequence we pick this way actually converges as a sequence in RK, right? Because all of the components converge. So that's the idea for the Bolzano-Weierstrass theorem in RK. See you in the next video.